All right, hi everybody. I'm going to go through number 59 from this week's homework, which is a follow-up to number 57 from last week's homework. And I actually have a video posted for that one if you had trouble with that and want to look at that one a little bit more closely before you do this one. So this one is actually a little bit different. This is sort of purely a vector addition or examining vector relationships problem, which is actually a great thing to get a little practice with. Okay, so in this one it says, in what direction would, keep knocking my video. In what direction would the ship in exercise 3.57 have to travel in order to have a velocity straight north relative to the Earth? So this is what we want our ship to do relative to the Earth. So we'll call this ship relative to the Earth. Assuming its relative speed relative to the water remains 7 meters per second. Okay, so we still have our current, which was, let's see, 1.5 meters per second, 40 degrees north of east. So it's like this. This is 40 degrees, and the length of this was 1.5. And then we need to figure out what, I'm going to move this vector up a little bit in the interest of a somewhat accurate scale. So I'm going to go ahead and make it this whole thing. Okay, and so then this vector is going to be 7. But we need to figure out what this angle is right here. So we can go ahead and call that theta. Okay. All right, so what do we do now? Well, we need to look at our components, right, and figure out what our x components and our y components are. But a really cool thing happens in this problem. We go east, so we go in the positive x direction for a little bit, and then we go to in the negative x direction right back to where we started. So our change in our x direction is going to be 0, which sort of makes the problem. It makes everything go a lot easier. So let's go ahead and call this the velocity of the ocean. Oh, sorry, so that's going to be 1.5 meters per second. And then we're going to do the velocity of the ship, and we're going to call that 7 meters per second. And then let's go ahead and write out our components. So if we look at the velocity in the x direction, we're going to need the x component of this one, which is right there. So if we look at our SOHCAHTOA, that's going to be our adjacent angle. So it's going to be 40 times, 1.5 times cosine of, oops, I just said I wasn't going to use 1.5. I was going to use V ocean. V ocean times cosine of 40 degrees. And then minus, because now we're going in the opposite direction. And then we have this one here. We're looking for the x component, so that's going to be right there. That's also adjacent, right? So it's going to be the same. So we're going to have minus Vs cosine theta, and then we know that this is going to equal 0. So that tells us that V ocean cosine of 40 degrees is the same as V ship cosine of theta. So then we can say V ocean cosine 40 degrees equals Vs cosine theta. Then I can divide by Vs, and I get cosine of theta equals V naught cosine, sorry, no, V ocean cosine of 40 degrees divided by the velocity of the ship. So I have 1.5 times 40 cosine divided by 7 equals that, and then that gives us that theta is 80 degrees, or 80.5 degrees. 80.6 degrees. And let's see, so that is going to be 80.6 degrees north of west. Okay, so that's our angle. That's the first part of the problem. Now they want us to figure out this. What is this length? So in order to figure that out, what we can do is just find our y component, because the speed of the ship relative to the Earth is the y component of our vector, because it's only in the y direction. So because none of it was the x component, the whole thing, the sum of our y components, is our vector. So if we find the velocity in the y direction, we should get what we need, right? So let's see. So we've got Vy is the velocity of the ocean times, we're over here now, so this is going to be our sine of 40 degrees. And then we're working together again, right? These are both going up. So plus velocity of the ship times, and now we're over here, so that's opposite, sine, and then we know 80.6 degrees. Okay, so now we just have to plug everything in. So we've got 1.5 times 40 sine plus 7 times 80.6 sine equals, and we get that the velocity in the y direction is 7.86 meters per second. And so the speed, the velocity relative to the Earth is 7.86 meters per second north. Right, so that is our solution to that one. I think that was a great follow-up to that one, because it makes a lot more sense that you wouldn't just go north on your ship and, you know, just kind of figure out where you end up based on the current. You would figure out what the current is and then figure out how you need to adjust your motion based on that. So this is actually a pretty sensible question for them to have asked, and it's great practice of dealing with vector stuff. So I hope that that was helpful, and thanks.